After studying the magnetic field produced by an electric current traversing a straight wire, now what happens if we wrap this wire into a coil or a solenoid? Basically, the magnetic field will be concentrated within the area or the region inside that coil, which here we call a solenoid. Why? A solenoid has a radius much less than its length. In a moment we will see its shape. It is formed of N loops and of length L. When it is traversed by an electric current I, it produces in the region inside the coil a uniform magnetic field whose characteristics are the origin. You can draw the magnetic field anywhere. It's going to be straight anywhere inside the solenoid. The direction is going to be along the axis of the coil or the solenoid, same thing here. The sense is given by the right hand rule, and we will see how. As for the magnitude, we need to memorize this equation. 4 pi multiplied by 10 to the negative 7, n, the number of loops, multiplied by I, the current, divided by length L. Now, here is a coil in which we wrap the wire in spiral shape or circles. You notice that when the current moves as shown here, the wires or the red line or direction showing the current is on the frontal side. Using the right hand, in which when you look at the figure below, the right hand holds the solenoid from behind. The fingers or the palm points along the direction of current I, then the thumb points along the direction of magnetic field B, which is upwards in this case. Let's move on to check in another scenario with more details about the right hand rule. While using the right hand rule, the palm holds the solenoid. Imagine yourself with your right hand holding the solenoid as if you are holding a certain pipe. And the fingers point with the direction of the current. The thumb points like the magnetic field inside the solenoid. Look at the figure here. The current is moving according to the direction positive to negative. Now, if you want to hold this coil appearing in front of you now, your palm is going to be on top of this coil, and thus the current is going to be pointing as shown in the figure. Then the magnetic field is going to be from right to left, or coming out from the left side. Thus the left side becomes north, while the right hand side becomes the south. Notice again that the palm here or the hand is holding the coil from behind. The same figure is shown below, but from two different angles. In the figure shown to the left hand side, we hold the pipe from behind. Notice the fingers point along the direction of I. In the right hand figure, in the right hand side figure, you notice that the hand holds the coil from the frontal part, then it wraps around the coil, and the thumb also points to the left hand side. Now, in case you want to draw that, this is a bit tricky. Keep in mind that we always draw the frontal side, because this is a 3D figure, as solid lines, while the rear side as dotted. Notice, frontal solid, rear dotted. Sometimes we draw the frontal side as more bold or thicker than the rear side, so that visually you understand it. Over here we have the same figure. Notice, magnetic field lines come into the coil from the right hand side. Inside they are straight, on the left hand side they exit. That means, looking at the coil, the right hand side is a south pole, as if it's a magnet of south pole, while the left hand side is the north pole. If you check that, looking from the right hand side, you notice that the side is S. If you follow the direction of the current, you can write letter S as in south. Now, try to solve this problem, which is a direct application on what we have seen so far. A solenoid placed on a horizontal table with its axis aligned with the magnetic meridian, which is the south and north axis. So here you have to draw the plane mimicking and showing the north, south, west and east directions. This might be a bit tricky in drawing, but it's simple. Draw a figure showing the setup as observed from a point vertically above the plane. Specify the direction of the needle placed inside the solenoid. Then a current I traverses the solenoid, and you need to calculate the value of the magnetic field of the solenoid. This is simple, direct application just to get used to the equations needed. Another nice application about this, just to make sure that you understand the fact or the idea of north and south poles of the loops of the solenoid, consider 4 different scenarios in which we have a magnet placed close to a loop. Now, when you look at the figure here, you notice that in each case, there is a current in the frontal side of the loop. If you notice, always the solid line is the frontal side. The magnet is placed somehow close to that. All you need to do is, knowing that like poles repel and unlike poles attract, specify the nature of each phase of the loop put near to the magnet, and then determine whether the magnet and the loop in this scenario attract or repel.